Hi everyone, and thanks for joining on the live stream or watching the recording. So today we're going to look at the last of my three sessions on EM, electromagnetic radiation, and quantum as based on the A-level physics syllabuses here in the UK. So last time we ended up looking at emission spectrums, and today we're going to look at absorption spectrums, although I want to just back up and talk a little bit about, well, you'll see. First of all, so here's our set of levels for a hydrogen atom this time. We spoke mainly about helium last time, and we were saying that in the textbooks they go up to and include kind of an infinite number of levels here, which would suggest that there can be an awful lot of these lines, whereas here in the visible spectrum for hydrogen we have a mere 4 lines. And the reason for that is because many of the drops are so big, like for example this one, that will produce a ray, or a photon I should say, in the UV section of the spectrum, which of course our eyes aren't sensitive to. So off up the top, if as it were, of this spectrum. Now it turns out that we can have several what they call series, and this is right on the edge of the syllabus here. So just imagine this: we have an electron dropping from 2 to 1, or from 3 to 1, or from 4 to 1, or any combination as long as it ends on 1. And that will make one big set of lines for us, and I believe that's known as the Lyman series. But the point here is that the drop from 2 to 1 is kind of included in every one of these drops, and this is a big change, which means that all these photons from these various drops that end in level 1 there, the ground state, are going to have high energy, so they're all going to be ultraviolet, and so this will create a series of lines that we can't see. And it turns out that the visible spectrum for hydrogen is created when we only look at drops that go to level 2, like this. Now, because I suppose because we don't have this big fat energy change here to include, the energies are much lower, meaning that they turn out to be visible in the visible spectrum for us. So I just thought I'd mention that as a interesting sidebar. If you do the astrophysics option in AQA, you'll definitely come across this idea some more. Right then, I want to talk about the mercury vapour lamp quickly. So mercury, as you know, is a metal. It's not a very nice metal. It's actually quite poisonous. So I'm not sure how easy it would be to buy a mercury vapour lamp these days. But nevertheless, AQA in their wisdom want you to know about them. So imagine we have a mercury vapour. Now that means we have a mercury atom like this in a kind of a gaseous state inside, or maybe tiny particles of mercury floating around inside a partial vacuum. And we then would have to put on a fairly hefty voltage, 1000 volts, something like that, such that any free electrons are in here are going to be accelerated rapidly, and then some of the electrons will be ionized off the mercury atoms, which will create a kind of a cascade, enabling us to have lots of excitations happening. And then what you find, rather annoyingly, is that the photons that are produced are all in the UV area of the spectrum. Now that's not much use to us. It's not much of a lamp, is it? Because we can't see UV. So this is solved by, rather cleverly, by adding this yellow layer of phosphor to the inside of the tube. So what happens now is that the mercury is excited, gives off UV photons as the electrons drop back to their original levels, and then the UV photons are absorbed by this layer of phosphor on the outside of the tube. And what the phosphor does is, obviously, it becomes excited and the electrons in its particles shoot up high, but then they fall back down in what's known as a cascade. So they go down the levels like this. And what that means is that a whole pile of lower energy photons are given off, which just happen to be in the visible side of the spectrum. So in other words, there's two processes going on here. We've got the mercury, which is producing very high energy ultraviolet photons for us, which are then absorbed by the phosphor and re-emitted as visible photons. You quite often get questions on this, so I thought I'd chuck one in. So there's some multiple guess. What is the role of mercury vapour in a fluorescent tube? Well, the mercury vapour is excited by electrons colliding with it. The mercury, the Hg, does not do any absorbing of photons or anything. So in other words, A is wrong because no, the mercury does not absorb photons, and so is B. But we then know that the mercury goes on to emit UV light. So it's not visible, and it is UV. Okay, so that's the answer to that one. Relatively straightforward, that. Right, now let's get on to the more interesting part for today, which is going to be a look into the wonderful world of absorption spectra. And we'll start off by just reminding ourselves of what a continuous spectrum is. So in a continuous spectrum, at least let's say a continuous visible spectrum, you have every possible colour, every photon, every energy of photon represented between the red end and the violet end there. So in other words, you have the whole lot. There are no gaps, and you get the rainbow effect effectively. Now it turns out that if you fire photons into a gas, then you will excite the electrons on some of those gas particles up to higher levels. And in the process of doing that, you are going to pull away those photons because they're going to be absorbed. So the mere process of a photon coming along, if this photon has that much energy, it has to have the right amount of energy, doesn't it? Remember that. So if this is a 10.2 electron volt difference between the level 1 and level 2 for hydrogen, like we talked about, if you have a photon that comes in which just happens also to have 10.2 electron volts, then that photon will be absorbed. It will cease to exist, and the electron will shoot up to the higher level, but only those photons with 10.2 electron volts. Now the upshot of all this is that if you get what is euphemistically known as white light, so white light, as I'm sure you know, is a continuous spectrum like this. So our eye will seal these colours together, and to us it appears as white, hence the name white light. So we take white light, and when we say white light, we mean every possible member of the spectrum is being shone onto that cloud there. And what that means in turn is that the white light, I don't know why, I appear to have got some extra lines that I am unable to get rid of here for some reason, which is nice and annoying. Let's see if I can do it like this. Maybe if I do that, I can get rid of them. No, these wiggly lines look like they're stuck. So I don't really know what's going on there. Can't rub them out. Oh, we're having a mare today. We are having a mare. Anyway, white light is shone into the cloud of dust or gas. Let's say it's just a dust cloud, probably in space. And then because in here we have atoms, the electrons in the atoms are able to jump to higher levels and will absorb very specific photons out of the white light. And so we end up with this extremely beautiful absorption spectrum, which is like the opposite of an emission spectrum, because here we now have the rest. What we see are those photons which are able to pass through the cloud, in other words the ones that don't get absorbed because they don't have energy that corresponds to a jump. So this is called an absorption spectrum, and because these spectrums are absolutely unique for particular elements, we can look at this spectrum. We can literally go to Google and say, show us all the spectrums, and we can compare the spectrum that we've got and identify what gas is in that cloud. And that's how we know these remarkable statements that people like astronomers say when they say there is an enormous dust cloud made of hydrogen over there, because they can see the emission spectra of the light that is coming through the cloud from a distant star, which when you think about it is just utterly awesome. So I'm just going to pause the stream for a moment and see if I can sort out this little issue. So I can do that by pressing this. So I managed to get rid of the lines just by closing PowerPoint and opening it up again, which is very exciting for you guys, isn't it, to hear about? So I don't know why I told you really. So anyway, here's a slide which combines an emission spectrum and an absorption spectrum. On the left we have our continuous spectrum. So let's just say this is in fact for helium gas. Helium. So this is the emission spectrum you get. So in other words, if you excite helium gas, it will give off just these lines. But if alternatively you shine white light through helium gas, then you'll get this lovely absorption spectrum. And as you can see, the absorption spectrum gaps correspond exactly to the emission lines. That means, therefore, that we have two ways to fingerprint helium by looking at the absorption gaps or the emission spectra, depending on exactly what we're trying to do there. Okay, so that's absorption and emission spectra. So then here's an interesting little question that I had about this for donkeys till one day this just clicked for me. So let's say we're an observer over here, and what we're doing is we are looking at a cloud of gas. I don't know, let's say it's hydrogen gas. I mean, what else is it going to be? And over here we've got some nice bright star. And what we do is we often say white stars or stars emit every frequency. I'm going to come to that in a minute. So we'll just assume then that in comes white light into this cloud. And looking over here, the observer there on planet Earth, they're going to see a very nice absorption spectrum like we've been talking about. But I wondered to myself quite a lot, how is it that if we have our helium atom in here, and our helium gets excited up to another level, like we've been teaching over and over again, absorbs a photon, I would expect to see an absorption line. But surely, I thought, surely the helium is going to then de-excite, fall back down where it started, emitting a photon of exactly the same frequency as the one that it absorbed, therefore filling the spectrum line, or the absorption line, back up, making the line kind of disappear. Interesting. So how can we see an absorption spectrum at all? And of course, with all these problems that you find yourself thinking about, very often it's blindingly obvious. In fact, it's so blindingly obvious you probably know this. Okay, so the white light is originally travelling in from the left hand side. Some of it goes through the cloud and arrives at the observer. Okay, fairly obvious. So let's get rid of that line. We then have our helium atom in the middle there, which absorbs a particular photon by doing that. Now, in the model that we know and love, these electrons are orbiting around a helium atom. So let's just pretend, for sake of argument, that it's over here when it de-excites. So really I should have drawn it in the outside level. It's this position. It now de-excites, emitting a photon off in that direction, which of course is never going to arrive over here at the observer. So yes, the light is re-emitted, but in the process it is effectively scattered off in all directions, because it's not just going to be upwards towards 1 o'clock, is it? It could be in any direction that the photons are re-emitted. So yeah, they are taken out of the spectrum, and this might explain why when you look at proper photographs, I mean I made these, but if you look at proper photographs of absorption spectrum like this, these black bars are not completely black. They're very much fainter, but have some of the colour there that's missing. In other words, a very faint version of this will be sitting in this gap. And I suspect that at least one reason for that is that some of the emitted photons, very few obviously, do make their way into the observer's eye. Now that's just my theory, I don't know if that's right or wrong, but it's a good theory and I like it. So another thing that's really interesting here is to think about the structure of a star, because you can learn a lot about this. Now surprisingly, if you do the astrophysics option, you'll get to learn all about this, but the inside of a star is a lot hotter than the outside of a star. So in effect, although the outside, I would not say go and touch the outside of a star because it's not cool, but relatively speaking it is cool compared to the inside. Okay, so that's that. What we can then say is that we can imagine that, let's shrink our star down, looking at the top diagram. Okay, now a star can be considered, or let's say the center of the star, to be what's known as a black body radiator. And what that means is it emits, so up on the side here we've got energy. So this graph, this top graph, is showing us by wavelength how much of each of the wavelengths of the electromagnetic spectrum are being emitted. And what you see is that it emits the whole spectrum. Now, in this particular case, this particular star emits an awful lot more blue light than, say, it does infrared. But nevertheless, it is going to emit some infrared. And at this point, it might be emitting some microwaves and radio waves. And then up on this side, we've got ultraviolet, X-rays and some gammas. But notice it's peaking in the visible. Okay, so you would expect the light from a star to look like this curve. But what you actually find is more like this. Now what's happening here is that all these different colours of photons, if you like, all the different photons from the spectrum are all coming flying out through the hot bit. They then get to the cool layers, the outer layers of the star, and when they get there, some of them, not all of them, only those that have the right energies correspond to energy level changes, are absorbed. And so rather than getting the rather beautiful theoretical curve like we got in the top graph, which is obviously just sketched, what you can see is absorption spectrums. Well, those little dips, you would have expected the curve to go like that, or maybe I should draw it like this, but actually it falls down and we get a bit like this where the level falls away. And then by looking carefully at these dips, believe it or not, you can identify what gases are in the outer layers of the cloud because they've been partially absorbed as the light comes out of the star. Now it never ceases to amaze me that we can look at the tiny bits of light coming out of a star. I mean, think how dim a star looks. And then we can take that light, shove it through prisms and diffraction gratings and find out what the layers of the gas are constructed, what they're made of in a star that's light years away. It's just awesome stuff. So that's another use for absorption spectrums. So to finish up then, one little more question, just so we can have another practice run at this before we get to the end of this part of the topic. So this is a nice question. I've spent quite a lot of time doing this on with various students over the years and in my tutoring work. So let's have a look. The diagram shows 4 energy levels of an atom drawn to scale. Well, that's interesting. Very often with these questions you'll get that they're not drawn to scale, so that's worth noting. These energy levels give rise to part of an emission spectrum. Okay, so we've got 4 levels, and notice that we've got these two here which are really close together. All right, very close together, as you can see. And then we've got a relatively big gap and an even bigger gap. And your task, should you choose to accept it, is to work out which of these patterns, A to D, corresponds to these levels. So the first thing I'd say is look and see how many energy drops you can have on this diagram. So let's start at the top level. We've got this one, whoops, and then we've got that one. Then if we start at the second level, we've got that one and that one. And then we start on this level and we have this drop. So these are all the possible transitions or drops that we can have. Oh, and I think I've got them all there. I was just thinking I'd missed this one, but it's there, isn't it? Okay, so there are 6 possible levels. So there must be 6 lines. 1, 2, 3, 4, 5, 6. So what you find is that questions C and D only got 3 or 4. So it can't be those. Now the question is it A or is it B? Well, the way to identify this, I'm just going to rub my lines out quickly. The way to identify this is to consider what's the effect of these two that are close together. So if we start at the top here, we're going to have one that drops let's lumber these. Now 1, 2, 3 and 4. We're going to have an electron that drops from 4 to 3 and also another one that drops from 4 to 2. And there's only going to be a small amount of energy difference between those two. So they're going to produce a pair of lines that are close together like this. But there's also a pair that are close like that. The question is then, do we have another option? Well, we do. So thinking about what happens as we go from 3 to 1 and 2 to 1, again, these two are close. So these two are going to produce another pair. And there it is, another pair. So the point is, unfortunately, the answer to this one is A. And it's A because we have two levels with two close lines falling from 4 to 3 to 4 to 2, and then two close ones going from 3 to 1 and 2 to 1. So that's how we can identify it's A. Okay, so sorry for all the technical problems today. It's been one of those days, but we got there in the end. Any last... I can see, Mr. Reek, that you are somewhat perturbed by that. Yeah, but it is 2. It is A, because we've got these... There are levels that fall to those two close ones that will emit photons, and then levels that leave those two close ones, also producing similar photons. So yeah, so hopefully that was useful. Okay, well, thank you for watching, and I'll be back, hopefully without the technical issues, very soon for your enjoyment.